over to the cloud.
Yes, it's okay.
Yeah. Okay. So we're there, we're recording. So this week, we are dealing with a topic called higher order polynomials, okay? What does that mean? Well, you know, in Unit 2, we started dealing with a relationship between a y and an x, where this x is only to the first power, right? And forgive me one sec. My dog is starting to growl because she sees something outside in the darkness, probably deer.
Oh,
Do you have deer in the Philippines?
we have, but in the forest.
Yeah, these
You cannot
guys are right
see.
in my backyard. These guys are just all over the neighborhood, and she can't help herself. So we have these when we have a relationship between a one variable, which we usually use y, and x, where x is only to the first power. You will probably remember from Unit 2 that we call that Unit 2, actually Unit 3 and 4, we call that linear. In Unit 3, we learned how to graph them. In Unit 4, we learned how to solve systems of these types of equations. And this equation, when built completely out, it can have like a coefficient, like a number in front of the x, like we can have like 2x, and there can always be a constant term, you know, like -1 or something like that. And you probably remember this as we called that slope intercept form of a linear equation, okay? And so that's, and these types of equations are lines. Are lines where this determines how steep it is, how much the slope, how fast it grows up. Does it grow fast? Does it go back? Does it go down? And then the 1 out here on the end shows us where it crosses the y-axis, right?
Yes.
Then we went into last week, we got into a new type of equation that we called quadratics. And a quadratic is where we have a relationship between y and x, but where the x variable is squared. So we learned that creates a different type of graph. Instead of creating a graph that's a straight line, it actually creates a graph that looks like this. We call it a parabola, right? We call it a parabola, but it's really just a U shape. And if this number out in front of the x squared is positive, then it opens up. But if the number out in front of the x squared is negative, then we know it opens up down. It opens down. It's an upside down U, okay? And then we learned about different forms of it that, you know, that would help us graph it. We learned that if we have our quadratic in the form some constant or some coefficient a times x minus h squared plus k, that we could look, and h and k would be where the vertex is, right? So this would be hk. And then if it opens down, it's going to look like this. And if it opens up, it would look like this. Okay. So what's important to note here is a couple things before we go into this unit. Remember that anytime where we have the point where the graph crosses the x-axis, we call that a solution. What I can't stand about mathematicians is they give these things too many names. They not only call it a solution, they also call it a root, and they call it a zero. They call it a zero because it's where y equals 0. Anywhere along this x-axis, y is going to equal 0. So they call it a zero. They call it a root of the equation, and they also call it a solution to the equation. And so this is true regardless of what kind of, I'll call it function we have, whether it's linear, whether it's quadratic, or whether what we're going to get into today, where we have these higher order polynomials that are even greater than the squared term, like we might have a cubic term or x to the fourth or x to the fifth or x to the sixth. In every case, when we talk about the solutions or the roots or the zeros, it's that place where the graph crosses the x-axis, okay, where that graph crosses the x-axis. And you can see in this one, it doesn't cross the x-axis. And so when we see that it doesn't cross the x-axis, we say there are no real roots, right? Again, roots being one of the things we call these intersections with the x-axis, okay? So again, we dealt with linear equations. We've dealt with quadratic equations. And now today, we're going to deal with higher order, what we call polynomials. So it could look like this. It can be y equals x cubed plus 2x squared minus x plus 1. That represents 1. It could be y equals x to the 7th minus 1. It could be y equals x to the 205 plus 2x plus 3. A higher order polynomial is defined by the highest power that the x variable is raised to, okay? It's defined by the highest power of x. And what we want to do today is we want to learn not too much about these types of things because they can be very complicated and there's so many to pick from. But we want to learn how to graph them. And how do we graph them? We use two primary things. The first, we define their end behavior. And I'll tell you what that means in a minute. And then secondly, we find their roots. Again, also known as the solutions or the zeros. These roots are the things, this is where the function crosses the x-axis. Okay? So what is a higher order polynomial graph look like? Well, let's take a quick look and see if we can figure one out here. Let me find right here. Like, let's take a look, not at this one, but let's look at this one. No, let's not look at that either. So look at this top one here, okay? On this top one, you can see as I weave out, you can see that the graph of this higher order polynomial of degree 7, right? This has,
Yes.
this highest order term is degree 7, that it starts and it comes up from the left. It comes up from the left and it goes up to the right. Okay, so let me do an easier one. Let's just do y equals x cubed, x to the 3rd power, right? And I'll shut this one off for now. I'll shut this one off so we can just look at the new one that we did. This is the graph of y equals x cubed. You notice again that it comes up from the left and it continues up to the right. So we would describe this end behavior is up on the left and up on the right. But what happens if I turn this into a fourth power? Okay, that's interesting. Now it goes down on the left and up on the right. Again, we're just describing the end behavior, meaning what does it do at its two ends? There's two ends to this function. There's a left end and a right end. Is it going down and is it going up and up on both? Is it going down on one and then up on the other? Or is it going down on one and then down on the other? That's what we're trying to describe. And I'm going to show you how to identify whether or not a graph is going to do that just by looking at its equation. Well, you probably will notice if I keep doing this, let's say I put a 5. Oh, well, the 5 looks like the 3, right? And what if I put a 6? Well, the 6 looks like the 2. So what we can say is we can say, and if I go back up here, what happens if I go back up here and look at the, I'll turn this one off and I'll go back up and I'll look at the one that's a 7. Well, the one that's a 7 is like the 3 and the 5 in so much as it goes up on both on the left and the right. Okay. I'm joining in. The students did finally join from Afghanistan. So there's 5 students that are popping in right now. I'm not sure if you'll see them or not, but just letting you know that they're here, Lorley. So you're not alone anymore. Okay. Give them a minute and see if they can. Sometimes I'm not sure if you have trouble too. They have terrible trouble with internet and it takes them a minute to join. And sometimes like they disappear and they come back and whatever, but I'll keep going. So what we know is we can see a pattern. And the pattern is if this exponent right here of the higher order term, again, the highest order term, remember, like if we look at this one, it has a 7 is the biggest one. And we care about what the biggest one is. We don't care about the 5. We don't care about the fact that this would be a 1, right? 2x to the first power. We don't care about those. We only care about the biggest one, the 7. If that highest order exponent is odd, it's going to have this kind of shape where it comes up on the left and continues up on the right. But if it's even, like this x to the 6th, if it's even, like a 2, 4, 6, 8, then you can see that it's going to come down on the left and up on the right. The end behavior will be opposite of each. Okay? So if I said to you, what is it going to look like? I'm going to turn it off for now. I'm going to enter raised to the 9th. If I put a 9 here, I'm going to turn this one off too. Y equals x to the 9th. What do you think it's going to look like? Do you think it's going to go like a U shape? Do you think, let me do this on my paper. Let me show you. If we look at x to the 9th, y equals x to the 9th, we see that this is odd. This is an odd number, right? And our odd numbers tend to go like this, right? But our even numbers, if we say y equals, put that in a different color, y equals x to the 10th, our even numbers where we have an even highest order exponent, they look like this. They go like this. They go, okay? And let's verify that. Let's take a look. If I turn this on, x to the 9th, yep, you see that it has that behavior. If I turn on an x to the 10th, you'll see that it has that behavior, right? I'll turn that one off. So you can just see that one. Now, it does do some other interesting things. The graphs will do some interesting things. Let's take a look at these versions of graphs up here, whose higher order terms are 7 and then 8. Okay? Now, we looked at the first one already, and we see that it goes up on the left and up on the right. Okay? Notice that if we have this term that has the x to the 7th, that has the largest exponent, if the number in front of it, the coefficient of that term, is negative, you may remember or think that from what we've studied in the past, putting a negative term in front of it usually just flips it. It creates a mirror image. So let's see what that does. Notice that when we flip this to a negative 3x to the 7th instead of just 3x to the 7th, it now goes down on the left and down on the right. It basically flipped it, right? So if I look at both of these together, you can see it flipped it. Okay? Now, what happens if I turn these guys off and instead do it to the 8th power? Same coefficients. We have a fifth. We have a power to the 5th here, a 2x and a 19. All we change here is making this go from a 7 to an 8. And now you'll see that it goes down on the left and up on the right. Okay, down on the left and up on the right. So just by making it an 8th power. And again, if I put a negative in front of the 3, it's going to flip this guy upside down, right? It's going to flip it upside down. You see how it does that? So first of all, before I turn this one on right here, this x cubed plus 4x minus 48, what do you think it's going to do? What do you think it's going to do? Do you think it's going to go up on the left and up on the right, which means it's going to go, if you can see my mouse, will it go like this? Or will it go down on the left and up on the right, like our U shape? Or will it go down on the left, down on the right? Which way do you think it'll go? Remember, it all depends on this being odd or even, right? So let me show you. We'll click on that, and you'll see that when I zoom out, it's hard to see, but it goes up on the left, and once it crosses the y-axis, it goes up on the right, okay? That's not a very good one because it's hard to see on the graph. But let's, I wonder if I should have done that maybe. Let me do that. And that's a little easier to see, but still not that easy to see. If I zoom terribly, then you can see the behavior a little bit better, right? But let's talk about, so now that we have a concept of end behavior, we're going to go back to my drawing here, or to my sheet. And I'll remind everybody, because I see that we have our team from Afghanistan that has joined as well, that where we left off is today we're going to talk about these higher order polynomials where they're defined by the term with the largest exponent, So in this one, this would be called a third order polynomial, but it has a a catchy name. We call it a cubic. We call it cubic because it has the third, where x squared would be, where x to the second power would be squared. Okay, x to the third would be cubed, but then we don't have fancy names anymore. This would just be seventh order. Okay, because this is to the seventh power. Suppose a polynomial passes through the following points. It passes through 5, negative 5. It passes through -5, 3. So there's -5, and there's 3. So it passes through there. It passes through -2 and -9. -2 and -1, 2, 3, 4, 5, 6, 7, 8, 9. So this is -5 and 3. This is -2 and -9. It passes through 0 and 6. 3, 4, 5, 6. 0 and 6. 1, 4. 1, 4. Okay. And it passes through 7, 8. 1, 2, 3, 4, 5, 6, 7, and then 8. 7, 8. So it goes here to here. And then the question asks, how many x-intercepts can you guarantee it has without any other information? Well, we have to connect the dots. We have to connect these points. And so if I draw a graph through these points, we draw a graph and we have to go left to right. So we're connecting this guy then to this guy, to this guy, to this guy, and then eventually to this guy. Now, we don't really know what happens in here. Maybe it goes all the way down and goes through the x-axis again. We don't really know that. But we know how many can we guarantee it has? How many x-intercepts can you guarantee it has? Well, we just have to count them. We know we have at least 1. Let me put those in a different color. Let me put those in red. We have at least 1, 2. So we have at least 2. And then it says, where on the x-axis would you find them? Well, you'd find them between the points -5 and -2 on the x-axis. And then you'd find them, and that's it. That's it. You'd find them somewhere here between -5 and -2. That's where this one is. And this one is between -2 and 0. So this is between, x is between -2 and 0. And this one, x is between -5 and -2, right? That's what we know. And then it says, what is the fewest number of points you can add to the list in order to guarantee it would have 6 or more intercepts? Well, you can see quickly that you could probably create a point. Let me get rid of this right here. Let me get rid of this right here. If we created a point here between this 0, 6 and 1, 4, between here and here, let's create a point here that's down here. Then you'll see that our graph would have to come from here oops. And then we would actually add another 2, right? We'd add this one and that one. Just by adding a single point. We can add a single point that would guarantee that we have 2 more. And then we could add 1 more point to guarantee that we could have even more, even 2 more. So I just want you to wrap your head around this idea that where the points are and when you connect the points determines, yeah, sure. That's fine. Where the points are and what the points determine is how many times the graph is going to cross the x-axis. Okay? So that's just an exercise that we do to start with. And now we're going to get into some of the worksheets that we're dealing with. Okay, going to get into some of the worksheets. So let's start by talking about polynomial long division. Okay, so what does it mean, long division? Well, if you think about this polynomial from the last chapter, something like this, a quadratic, y equals x squared plus 2x minus 8. We know we can factor that, right? We know we're looking for values whose product, when you multiply them together, is -8, and whose sum is +2. Well, that's going to be -4 and x, +4 and x minus 2. Because -2 times +4 is your -8, and x times x, and when you add them together, you get a +2. So we already know that. We know that the factored version of this polynomial, we know that the factored version is this. But what if we didn't know that we had this? We knew one factor. We know one factor, but we don't know the others. What if we only know the one factor but don't know the others? Then we could actually find the other factor by dividing this into this, right? Because division is the opposite of multiplication. So we know that if we multiply it by x minus 2, then if we divide it into here, we should get x minus 2 out as a result. So let's try and learn how to do long division of polynomials. And it's very, very similar to doing long division of numbers, right? We remember if we're going to put 3 into 180, 9, and 3. Let's say we're going to do that. 3 into 18 goes 6 times. 6 times 3 is 6 times 3 is 18. We subtract, we get 0. We bring down the 3. 3 times 1 is 3, and we have a remainder of 0. So we have 61 times 3 equals 183. That's a reminder of how to do long division. Now let's do it with polynomials. Let's do it with polynomials. We have x squared plus 2x minus 8, and we want to divide that by x plus 4 to see if we can find this other factor. Well, how many times do I need to multiply? What do I need to multiply x by to get x squared? Well, we have to multiply it by x, right? So I'm going to put that over here above the x term. X times x is x squared. And x times 4 is a positive 4x. Okay? Now we subtract them. And I just change the sign whenever we're going to subtract to show how to do it. To make sure we get it straight, I make sure I show a different sign for subtraction. And then we're just going to put these together. X squared minus x squared is 0. And 2x minus 4x is a negative 2x. Now we bring down our -8. And now we ask, what do I need to multiply x by to get -2x? Well, I need to multiply it by -2. -2 times x is -2x. -2 times 4 is -8. And when we change our signs, this goes away, this goes away. We have a remainder of 0. So we now know that our extra factor is x minus 2. Okay? So we just use long division to find the extra factor. So why don't we try another one? Why don't we try this one here? Sometimes it won't come perfect. It won't divide perfectly, and we have a remainder. And I'll show you how to do that. Okay? Well, I think we lost our other group. So Lauralee, it's just you and me again. We lost our team from Afghanistan. Here they come. They're back in. They have such bad internet. It just jumps back and forth. So here, let's talk about how do we do this one. 4r² minus 11r plus 12, and we're going to divide that by r plus 8. Okay? Well, the first thing we do is we say, what do we multiply this by to get this? Well, we need to multiply it by 4r, because 4r times r equals 4r squared, right? So we need to multiply it by 4r. We're going to put this over here. We're going to keep it aligned, the r terms with the r terms. So if we multiply 4r times r, we get 4r squared. That's this times this. And then if we multiply 4r times 8, we get a positive 32r, right? And then we subtract. And these 4r's go away. They become 0. 4r squared minus 4r squared is 0. Okay, this is 0, but I won't write the 0. And then negative 11r and negative 32r is negative 43r. Okay, now we say, what do we multiply r by to get negative 43r? Well, we multiply it by negative 43. Negative 43 times r is negative 43r. Okay, oh, we got to bring down our 12. Sorry, we got to bring down our 12. Oops. So we always bring down that extra term. And now we say, what's negative 43 times 8? Negative 43 times 8. Well, that's 24. Carry the 2, 32, 34, but it's going to be negative, minus 344. We have to subtract these each, so we change the signs. This becomes a plus, and this becomes a plus. 43, negative 43 and a positive 43r goes to 0, but I won't write that. And then 12 and 344 goes to a positive 356. And so we're left with a remainder of 356 divided by this as our denominator, r plus 8. So that's how you do long division. Just like you do it with little numbers, we do it with polynomials. We do long division with polynomials. There's one more we can try if you want. Let me see how we're doing on time. Does it make sense? Lauralee, does it make sense, the long division? Yeah, yeah. How about folks in Afghanistan? Can you see me in the Koshak Center? Anybody there? Can you guys hear me? I want to make sure you're doing okay. I see you.
Yes, yes.
And
Okay.
does the long division make sense? Is everybody good there with long division?
Yes.
Okay, sounds good. Well, I'll run through this next one very quickly. I'll do it anyway, just because I want you to be able to see, to have the benefit of it. R cubed plus 5r squared plus 10r minus 5. And we're going to divide that into, we're going to divide that by r minus 6. Okay, so let me grab this and move it over so we don't confuse things. Okay. So we'll do this one quick. I'm going to do this one quicker so we can move on. So r goes into r cubed 3 times, right? Or 2 times. R times r squared is going to give us this r cubed, right? So we're going to do that. We're going to say it's times r squared. R squared times r is r cubed. R squared times negative 6 is negative 6r squared. We are subtracting, so we change our signs. These go away, and this becomes 11r squared. We bring down our 10r, right? Now we do the same thing. What times r is going to equal 11r squared? Well, it's 11r. 11r times r is 11r squared. 11r times negative 6 is negative 66r. We're going to subtract these, so we have to change the signs. These go to 0, and then 10 plus 66 is 76r. Bring down our negative 5. And now we do the same thing again. What times r equals 76r? Wait a minute, did I do that right? 11r squared. Yes, what times R equals 76R? It's just
76.
76, right? Just 76. 76 times R is 76R. 76 times -6. Well, let's try that. What's 76 times a -6? 6 times 6 is 36, carry 3. 42 and 3 is 45. Negative 456. We change the signs. These go to 0. And then -5 and a positive 456 is a positive 451. That's what we have as our remainder. 451 divided by R minus 6, right? And that's what we're left with. This is the answer to our polynomial long division, okay? So you shouldn't have any trouble. That's all from worksheet 1, worksheet 6.1. It's all about the polynomial long division, okay? You guys will have no trouble with that. So let's move on from, and the reason we do polynomial long division is so we can find a different factor. If we have one factor and we need to find another factor, we can long divide the one factor into the original polynomial. Okay, and so you'll see that coming back again. or to describe the graph of a higher order polynomial, we need to know where it crosses the x-axis. We need to find its zeros or its roots. Where does we need to find where the graph of the function crosses the x-axis. Okay? So that's what a zero is. A zero, a root, a solution. So if we can say, because we learned this technique when we did Unit 5, or actually, yeah, Unit 5, where if we have f of x, a function, is made up of the following factors: x minus 3, 3x minus 1, excuse me, plus 1, and x plus 1, we know that it's going to cross the x-axis whenever f of x is f at 0, is 0, right? When we have a graph, all these points, what do they have in common? Y equals 0. So we set our function f of x or y equal to 0. And then if this is the case, then we know that one of these at least must be 0, because 0 times anything is going to be 0. So if this x minus 3 is 0, we know this will evaluate to 0, because 0 times this is just going to equal 0, right? So you probably remember this from Unit 5, where when we factor, we set each of the factors equal to 0. So x minus 3, so we want to say for this to equal 0, what must be true is x minus 3 must equal 0, 3x plus 1 could equal 0, or x plus 1 could equal 0. So x would equal 3. X would equal, this is, if we set this equal to 0, oops, I meant to say equal 0. This would be negative 1/3, negative 1/3, and then this would be x equals negative 1. Those would be where it crosses the x-axis. And you notice, and just to kind of circle back to the graphing of it all, we can say that we have roots at 3, at negative 1/3. So negative 1/3 is going to be like right in here. Okay, and negative 1. And we know that this is going to be a cubic. It's going to be to the 3rd power. X times x times x is x to the 3rd. So our highest order power is going to be x to the 3rd. X to the 3rd, this is odd. So we know our end behavior is going to be the same, right? Either up and up or down and down. But we do not have we have a positive coefficient out here. This is like saying this whole thing is multiplied by 1. And since 1 is positive, we know that it's going to be up and up. So this polynomial is going to look something like this. Where this is going up and this is going up. And again, the reason it goes up and up and not down and down is because this coefficient is a 1. If this coefficient were a negative 2, which it's not, but if it were a negative 2, then you'd see it going this way. Right? If that were a negative, but it's not. Okay? So this is what it looks like. Now, let's find the zeros of this other one. So let me get rid of some of this. How about f of x x times 5x minus 2 times x squared plus 1. Okay? Well, we know we want to set each of these equal to 0. We're going to change this to be 0. Not f at 0. That was wrong. This is really, we're setting the whole equation equal to 0. So this means x equals 0, right, for that. 5x minus 2 equals 0 for this. And then x squared plus 1 equals 0 for that. Well, here x equals 0. This one, x equals negative 2/5, right? And this one's a little trickier. What's x squared plus 1 equals 0? Well, that's x squared equals negative 1. Well, now we're into imaginary numbers, right? If you plug this in, let's take this guy, x squared plus 1, and put it into the quadratic formula. Minus b plus or minus square root b squared minus 4ac all over 2a. We can do that. Well, a equals 1 because there's a implied coefficient of 1 there. B, there is no b, right? There's no x term. And then c is also 1. So we say negative 0 plus or minus the square root of b squared, which is 0 squared, minus 4 times 1 times 1 divided by 2 times 1. So what does this equal? It equals plus or minus, because the 0 goes away, right? Plus or minus the square root of negative 4 divided by 2. Well, what's that equal? Let's rewrite this negative 4 as 4 times negative 1 divided by 2. Well, when we do that, what do we get? We can pull this square root of 4 out as a 2, and we still have the negative 1 inside, divided by 2. Well, this equals plus or minus, these cancel, square root of negative 1, and we know that the square root of negative 1 equals I. It's the imaginary number I, okay? That's a complex number. The square root of negative 1 doesn't really exist in real numbers. It only exists in the complex numbers. So our final answer is plus or minus I. Okay, so our final answer is I and negative I. Okay, so there you go. So this x equals I and negative I. And those are our solutions and our zeros for this polynomial. So this question asks, write a polynomial function of least degree with integral coefficients that has the given zeros. Well, we know that x equals 3, x equals 2, and x equals negative 2. Well, if this is the case, then by just looking at what happened here, we can say that its factors must be, the factor for this one must be x minus 3, because when x minus 3 equals 0, x equals 3, right? So we know that it must have a factor of x equals 3. This one means we must have a factor of x equals 2. And this one means we must have a factor of x equals negative, this is x minus 2. And then this one, it must be x plus 2. Okay? So we know what the factors are, and that's all it's asking. What is the function? If we set that equal to a functional notation and we say f of x equals this function, then we can multiply it all out if we wanted to. We could multiply it all out and we would get that function. So let's do that. What's x minus 2 times x plus 2? Let's do this part first. This is x squared minus 2x and a positive 2x go to 0. I'll write it anyway. And then a minus 2 times negative 2 is negative 4. So this piece is x squared minus 4 times x minus 3. Okay? And so now we can simplify that. What is x squared minus 4? Well, let's just FOIL it out. X squared times x is x cubed. Negative 3x squared. Negative 4x. Positive 12. Right? So this is our final polynomial. This is it. This is f of x. Just by knowing the zeros, knowing where the graph crosses the x-axis, allowed us to find out what the equation of that polynomial is. Okay? And then so it says find all zeros by factoring each function. I'm just going to do one of these because I want to make sure you understand that we can use polynomial long division to solve this. Well, actually, we don't have to in this one. This one's pretty complicated. This one is the sum of perfect cubes. So let's do 15. If we take 15 and say f of x, we're going to do this one down here. F of x equals x cubed minus 2x squared plus x. And it's asking us to find all zeros by factoring. How do we factor? Well, what common factor can come out of here? We have a common x, right? So f of x equals x times what? Well, x times x squared equals x cubed. X times, we take an x out of negative 2x squared, and we get negative 2x. And then we get a plus 1 when we divide x by itself. Right? And so now we can factor this guy. Factor this guy. Well, we need something whose product, a number whose product is 1, but whose sum is negative 2. Well, that's negative 1 times negative 1. X minus 1 times x minus 1. So now we have its full factorization is x times x minus 1 quantity squared. Well, let's before I make that quantity squared, is that all it wants us to do? It says find all zeros. Well, now if we set this equal to 0, then we have, if we set this equal to 0, then we have x equals 0. We have x minus 1 equals 0. And we have another x minus 1 equals 0. So we have x equals 0, x equals 1, x equals 1. So our roots, okay, also known as zeros for f of x, are x equals 0 and 1 and 1. Well, when we say 1 and 1, we actually write it like this. We say 1 with a multiplicity. That means there's more than one of them, of 2, because we have 2 of them. So that's how we say it. We say our roots are 0 and 1 with a multiplicity of 2, because we have 2 1s, right? Because this was a squared, an x minus 1 squared. Okay? So that's how we factor, polynomials. And again, this one right here, this next one, x cubed plus 8, this has a special form, which is, it's the sum of perfect cubes. I wouldn't expect you to know how to do this, but you'd have to find it in like a book. So I don't want you to worry too much about this one on the worksheet. I'll go ahead and give you the answer for it. When you have a sum of perfect cubes, it looks like, let me show you what it looks like. Here we go. this is going to look like, this is the same as f of x equals x cubed plus 2 cubed, right? 8 is 2 cubed. And so when we factor this, we get, this is x plus 2 times the quantity x squared minus 2x plus 2 squared. Okay, so this is going to be x plus 2 times x squared minus 2x plus 4. That's how we factor that. Okay, and then of course this is going to be a negative. This one is going to factor to become x squared, or excuse me, x minus 2 times x minus 2. Is that right? No, that's not right. X minus 2x. We need product that equals 4 and the sum that equals negative 2. So I think we have to take that to the quadratic formula. So what we would have to do to further factor this is we put it in the quadratic formula. And I know you know how to do that because you did that in chapter 5. So I'll leave the rest of this as an exercise for you guys. Okay? Just because I want to move on because we have some other stuff we need to cover. So that's how to factor and find zeros. Now we have these questions about polynomial roots from graphing. What else do we have to figure out? This is the next worksheet. This is worksheet 6B. And this one's not too bad. What this is telling us is it's saying, how do I find out what the roots are just by looking at the graph of a polynomial, of a higher order polynomial? Well, it's easy. The roots are where it crosses the zeros, where it crosses the x-axis. Here, 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 and here. So the roots are going to be, this is x equals, this is negative 3. This is negative 1. This is 1. And this is 3. Okay? So that's all that wants us to do. And how about this one? Well, we got one here, and here, and here, wherever it touches the x-axis. So this is x equals negative 1. That's that guy. And 0. And 3. So those are the roots just by looking at the graph. All you got to do is find out where it crosses the x-axis to find out its roots. So these things are called the roots, right? These things are called the roots of the function. Now it says for these exercises, for these two things, for these two where we have this and this, what is the polynomial in exercise 1 above? No roots are repeated, and f of 0 equals 3. Well, that means we have to put this into factors. Okay, we have to put this into factors. And so let's do that. What is this function going to be if the roots are negative 3, negative 1, 1, and 3? F of x, I'll use the red because that's what I was using. F of x equals x plus 3. That's the factor for the root negative 3. X plus 1, that's this one. X minus 1, that's this one. And x minus 3. Now we can multiply this whole thing together and get one really long polynomial, okay, if we wanted to do that. And let's see if we can do that. I have that written down somewhere. I don't want to go through it all again. Let me see where I put it. minus 3, because that's a lot of effort. You guys are going to spend a lot of time multiplying polynomials this week. And I don't know if that's going to be fun or not for you. Let me see. X minus 3, x plus 1. Well, you know what? Maybe I'm just going to do it because I can't seem to find it here on my paper. Oh, wait. Yes. So if we multiply all these guys together, we're going to end up with f of x equals x to the 4th minus 10x squared plus 9. But then it tells us, let me bring this down so that we can look at this together. Then it says f of x is the polynomial, no roots are repeated, and f at 0 equals 3. Well, if f at 0 is evaluated as 0 to the 4th minus 10 times 0 to the squared plus 9, well, that actually, if I just plug in a 0, that actually equals 0 minus 0 plus 9. That equals 9. But we know that it equals 3. Well, what do I need to do in order for this to actually equal 3? Well, this needs to be multiplied by 1/3 out front. So we come up here and we say this whole thing is multiplied by 1/3. Now, when we evaluate f at 0, we have 1/3 times 9, which equals 3. And that meets f at 0 has to equal 3, which is this condition here. Okay? I know that's a little weird. What I did there, let me just take you through what I did to make sure you're not confused. Okay? What I did there is I took this polynomial, and the reason I came up with that polynomial is because of its roots. Each root maps to a factor. Each root maps to a factor. Once I have all the factors, I multiply it all out. When I multiply all of these factors together, I get this big polynomial, x to the 4th minus 10x squared plus 9. That's what I get when I multiply all these together. And so now it tells us that f of 0 has to equal 3. So if f of 0 has to equal 3, that means we must have a 1/3 constant that this whole thing is being multiplied by in order for it to actually equal 3. How do we know that? We evaluate it at 0 without the constant, and we get 9. What do we need to make 9 3? We need to multiply it by 1/3. So that's how you solve a problem like that you're going to see on your worksheet. That's a little trickier, but just work hard on understanding the relationship between the roots and the factors. That's important. Relationship between roots and factors. Right? So if I have a root of x equals 1, I have a factor of x minus 1. Right? If I have a root of x equals -2, then I have a factor of x plus 2. That's what's really important here. Know the relationship of roots to factors. Okay? Now, here's another one that could be equally as challenging. Let's see. Given that -4 and 2 are roots of this polynomial, give its complete factorization and find its other root. Well, if -4 is a root, what is its factor? -4 means that if x equals -4, which means it crosses the x-axis at -4, that means that x plus 4 is a factor, okay? And it also means that x minus 2 is a factor. So we know that x plus 4 and x plus 4 and x minus 2 are factors, and we have this really, really long polynomial here. How do we find the other factors? Well, we can find the other factors by dividing. So let's multiply this guy together first. This is going to be x squared plus 4x minus 2x minus 8, which is x squared plus 2x minus 8, right? When we multiply these two guys together. And then we divide this into this whole big mess, 3x to the 4th minus x cubed minus 36x squared plus 60x minus 16. Now we're going to do this polynomial long division. Move this out of the way so you don't get confused. We're going to do this polynomial long division now. And this is why we practiced polynomial long division, so we can conquer something like this. So how many times does x squared go into x to the 4th? Well, it goes in x squared times, right? But we need 3x to the 4th, so it goes in 3x squared times. 3x squared times x squared is 3x to the 4th. 3x squared times 2x is a positive 6x cubed. 3x squared times -8 is -24x squared. We are now going to subtract, which means we need to change signs on these other guys. This goes to 0. We have -7x cubed and a -12x squared. We bring down our 60x. And we do the same thing all over again. How many times, what do we need to multiply by x squared to get to 7x cubed? To get to -7x cubed? We need to multiply it by -7x. Well, -7x times x squared is -7x cubed. -7x times 2x is -14x squared. Okay? And -7x times -8 is a positive 56x. We subtract again. These go away. -12 and a positive 14 is a 2x squared. Positive 60 and -56 is a plus 4x. Minus 16 is left because we bring that 16 down. And now we're almost done. What do we multiply by x squared to get 2x? What do we multiply by x squared to get 2x squared? We multiply it by a positive 2. 2 times x squared is 2x squared. 2 times 2x is a positive 4x. And 2 times -8 is -16. When we subtract, these all go away. And we have a remainder of 0. So what does that mean? That means we have another factor of 3x squared. 3x squared minus 7x plus 2. So we now have the following factors, right? Remember, what went into this factor? How did we get this factor? We got it from x plus 4, x minus 2, our two roots, right? So we have an x plus 4, an x minus 2, right? These guys. And now we need to finally factor this, and we will have all of our roots together. So how do we factor 3x squared plus, minus 7x plus 2? How do we factor that? Well, we're going to do this by finding values that multiply to become 6, and they add to become -7. Well, what is that? Two factors, it's going to be -6 and -1, right? -1 times -6 is a +6. -6 plus -1 is a -7. So we're going to use -6 and -1. So it's going to be 3x. Now we do by grouping. 3x squared minus 6x minus x. So all we're going to do is rewrite this -7x as -6x minus 1x. Okay? And 1x is just x plus 2. Once we do that, we can now group the terms. And here we have 3x squared minus 6x. We can take out a 3x. And that's going to leave us with x minus 2. And here we can take out a -1 out of these guys. And that's going to give us a minus x minus 2, right? And so this is going to be basically like a 1 here, right? So we can now take out our x minus 2 as a common factor. So we have x minus 2 as a common factor. And then what's left? 3x and -1. Now we have 4 factors. Now we have all of our factors, right? We have these 2 factors, which I will actually bring up to join our other factors. So this now becomes this. And we have all 4 factors now. Now that we have all 4 factors, we can find our missing roots. We knew our roots here were -4 and 2. Well, we have a 2 twice. These are the same, and we have a 3x minus 1. So this is x plus 4 equals 0. X minus 2 equals 0. We're just setting the whole polynomial equal to 0 and finding our roots. Okay, so now that we have all of these that we're going to go calculate, we will find our roots. Well, we already knew these were x equals -4, x equals 2. Here's another x equals 2. And this is going to be 3x minus 1. This is 3x equals 1, x equals 1/3, right? So our final answer is it asks us to find a full factorization. This is the full factorization. And these are the missing roots. We had our -4 and our 2. We have the 2 twice. And then we have x equals 1/3 is our missing root. Okay, x equals 1/3 is the missing root. That's how you do an exercise like number 9 on worksheet. Which worksheet is that? That is worksheet number 6B. This is all on worksheet 6B, right? I think I said that already. All on worksheet 6B. So let's finish up today. Let's finish up today by going through some questions like you might see on the quiz. And this is where I think it will really help you to sort of synthesize and pull together this information. And then we'll be finished up. Okay? Let's talk about these questions. Is there a solution? Is there a solution to the higher order polynomial x cubed plus 3x minus 15 equals 0 in this interval. Well, what does it mean, solution? It means solution is where y equals 0. So what we can do here is we can test the endpoints to see if one is positive and if the other is negative. Because if you have a graph and you have a point here and a point here, you know that the graph at some point through there is crossing over the axis and there will be a root, right? That's the whole point. If one is below the x-axis and the other is above the x-axis, then you know that the graph must cross the x-axis to get to it, right? So we have this function, and it wants to know whether or not there is a 0, a solution between x equals 2 and x equals 3. It wants to know if there's something in here. Well, that means we need to test to see if we evaluate 2, is it one side of the x-axis, and if we evaluated 3, is it at the other side? It could also work if it was here and here. We just have to find out if they were opposite signs, right? If they are opposite signs. So that's all we have to find out. So what do? We plug in 2. Let's plug in 2, and we'll plug in 3 and see if we get one negative and one positive. So f at 2 equals 2 cubed plus 3 times 2 minus 15. This is 8 plus 6 minus 15. This is 14 minus 15. This equals -1. What about f at 3? What does f at 3 equal? Well, that's 3 cubed plus 3 times 3 minus 15. This is 27. 3 cubed is 27 plus 9 minus 15. This equals 36 minus 15. This is definitely a positive number. It is 11, 20, 21. So we have -1. So this is what the graph looks like, right? So you've got a graph where you have f at 2. F at 2 is at -1 on the y-axis. 1, 2. F at 2 is at -1. But f at 3 is at 21. F at 3 is at 1. We'll call this 10. We'll call this 21. Way up here. F at 3 is way up here. So yes, there is absolutely a root, because in order for the graph to connect, it has to cross the x-axis right there. So that tells us that there is a root between those two values on that interval. Okay? That's how you solve that one. Suppose x is a polynomial with the following properties. Okay? For this, the graph must have how many intercepts? Well, let's get into this. How many intercepts? Well, we know that every time the graph changes from going positive to negative or negative to positive, whenever it changes sign, right, that we're going to have, whenever we have a change in sign, we're going to have it crossing the x-axis. Let's look at this. F at 1 is 10. I'm just going to be really rough on this because I think you guys get the point. So let's say f at 1 is 10. All right, so f at 1 is going to be 10 up here. F at 2 is -3. F at 2 is down here. F at 3 is -12 down here. F at 4 is 8. 3, 4 is 8 up here. And f at 5 is -28. Way down here. So what we have is we have through here, back up to here, and back down to here. So we have one that's happening between these 2 points, one between these 2 points, and one between these 2 points. Well, we can easily see that just by looking at where the sign changes. Does the sign change from 10 to 3, negative 3? Yes, it does. Does it change from negative 3 to negative 2? No, it does not. Does it change from negative 12 to 8? Yes, it does. Does it change from 8 to negative 28? Yes, it does. So it changes sign once, twice, 3 times. That means there must be at least 3 x-intercepts. And that shows you what we saw here. 1, 2, 3, right? So these are kind of easy to answer. We just have to look to see how many times it changes signs as we go from point to point. Okay? I think you guys hopefully got that one. Count the number of times it changes signs. That's what you do. Okay? Given that x equals negative 2 is a 0 of this polynomial, what are the other two? Are the other two zeros x equals 2 and negative 4? Well, we can test these values right in the function to see if it evaluates to 0. So does f at, what is the first one, 2? Does f at 2, what is that? Does that equal, does that end up equaling 0? So 2 cubed minus 2 times 2 squared minus 5 times 2 plus 6. Well, that's 8. 2 times 4 is 8 minus 8. 5, that's 10 plus 6. This is 0 minus 10 plus 6 is negative 4. No, it does not equal 0. Not equal to 0. So it is not a 0 of the function. Let's try the other one. F at 4, what is that? 4 or negative 4? F at negative 4. So negative 4 cubed minus 2 times negative 4 squared minus 5 times negative 4 plus 6. So this is going to be 4 times 4, 16, and 4, 64. This is going to be negative 64 minus what's negative 4 squared is 16. 2 times 16 is 32. Plus 20, right? These signs cancel, become positive. And then plus 6. Negative 62 minus 32 is negative 96 plus 26 equals negative 70. This is not equal to 0, so they are not. So negative 4 is not a root or a 0. Right? Zeros and roots are the same thing. It's just a different name for it. Okay? That's that one. You just test it in the function. Just test it in the function. When it asks you, is something a root of the function or is something a 0 of the function? Is x equals 2 a function, a 0 of this function? Just plug it in and see if it evaluates to 0. If it does, then it is a 0. If it doesn't, then it's not. Okay? Where does the polynomial function this cross the y-axis? Does it cross the x-axis at 0.30? How about 20? Well, how do we solve this? We evaluate the function at 0 to see where it crosses the y-axis. So f at 0 equals 0 minus 0 minus 4, if we put 0 in. And so yes, so where does it cross the y-axis? Negative 4. Right, that was just putting in 0. F at 0 equals 0 cubed minus 0 squared minus 4 equals negative 4. So negative 4 is where it crosses the y-axis. Okay? Then it says, does it cross the x-axis at the point 3, 0? Well, again, this is asking, is 3 a root? Is 3 the point where it crosses the x-axis? We can just plug it in. Evaluate f. We can just evaluate f at 3 and f at 2 to see if it crosses the x-axis at these points. So when we plug in for 3, we find out that no, it does not. When we plug in for 2, we find out that yes, it does equal 0 when we plug in 2. So x equals 2 is a root, but x equals 3 is not a root. Okay? Again, lots of times what you're going to do on this quiz is you're just going to plug in the value that it's asking you, whether or not it's crossing the x-axis there. If it asks you, does it cross the x-axis at 3, 0, you just plug 3 into the function and see if that value comes out to be 0. All right. Describe the end behavior of the following polynomial functions. We talked a lot about this today. If the exponent, the first one is y equals 3x to the 5th minus 2x squared plus 5, we look at the biggest exponent. If it is odd, then it is going to be the same. If odd, the behaviors will be, the opposite. One up will be one up and one down. And it's going to go up and down because the coefficient in front of the x term is a 3, which is positive, not negative. So since 3 is positive, it's going to go up and up. Wait a minute. If odd, end behavior will be opposites. If even, end behaviors will be the same. I think I have that wrong. If odd, end behaviors will be the same. If even, end behaviors will be the opposite. So this is going to be up and then up, right? And so just look at the end behavior. This should say odd, and this should say even. I typed this wrong. Okay. And then if the coefficient of the highest order term is negative, which it's not here, but if it is, in this one it is, you flip it. So instead of it being up and up, it's going to be down and down. Or if it's even, this one, negative x to the 8th is our highest term. Normally, x to the 8 would be down then up, right? Down then up, because it's even. But because we put a negative out front, it flips upside down and goes up, then down. Okay? All right, we're almost there. Consider this polynomial. If one factor is x minus 5, what is the other factor? If one factor is x minus 5, what is the other factor? Well, we just divide it into it, and we do our long division. X minus 5, we divide that into x cubed minus 4x squared minus 25. I think I've shown you long division enough. I don't need to show you that, but when you do this long division out, you're going to find an x squared term, and you go ahead and figure out what that factor turns out to be to determine what it's, the answer to this division is going to be that factor. In fact, I can probably do it pretty quickly here. X minus 5. So how many times does it need to go to x cubed? 4x squared. This is going to be x cubed minus 5x squared. We make this a plus. This becomes an x squared minus 25. This is going to be a x, or this is going to be a plus x. X times x is x squared. X times negative 5 is negative 25. We have a remainder of 0, which is good. X squared plus x is the other factor. If x squared plus x is a factor, then we can factor this further, and it becomes take out an x, and we have x plus 1. So we have x equals 0, x equals negative 1, and of course, x equals negative 5, which was this factor here, right? So our other factors are x equals 0 and x equals negative 1. It actually should say determine the other factors, because there's actually two other factors. It's x equals 0 and x equals negative 1. All right, what about this one? If f of x is a polynomial and f of 3, f evaluated at the value 3 is 0, what can we say about roots and factors on the graph? Well, if f of 3 is 0, then x equals 3 is a root, right? And if x equals 3 is a root, then we know x minus 3 is a factor. This is this ability to go back and forth between understanding what a root is and a factor is. If a factor is x plus 2, then its root is x equals -2, because we just set x plus 2 equal to 0. If we have a root of x equals -17, then we know that its factor is x equals, we know that its factor is x plus 17, right? That's how we go back and forth between roots and factors. And that's what we've been doing all day, okay? Now, lastly, factor the polynomial. Or we got two more left. Factor the polynomial y equals x cubed minus 6x squared plus 5x to determine its solutions. Well, we can factor x out first. So there's a common x in each of these. So we say y equals, take out that common x, and we're left with x squared minus 6x plus 5, right? All we did was we factored out a common x. And so now we know determine its solutions. Its solutions are its roots. So we know x equals 0. And then we have this guy, which is also going to equal 0, but it factors as well. That's going to factor to become x minus 5, x minus 1, because we need to have factors that multiply to get to positive 5 and add to get to -6. Well, that's -5 and -1. So now we have x equals 0, x minus 5 equals 0, and x minus 1 equals 0, right? So that's this, this, and this. So x equals 5, x equals 1. Our three solutions are 0, 1, and 5. X equals 0, 1, and 5. Those are the solutions, right? Those are the solutions. Last question. Does the polynomial f of x equals 2x to the fourth minus 3x squared plus 5x minus 8 have x minus 1 as a factor? Well, if x minus 1 is a factor, then x1 equals 1 must be a 0. Remember, x minus 1 is a factor, then we set that equal to 0, and we get x equals, if we set x minus 1 equal to 0, we get x equals 1 as a root or a solution, right? Or a 0. We're calling it zeros here. So we simply evaluate, if we know what the factor is, we evaluate the root, f at 1, to see if it equals 0. So what is f at 1? Well, 2 times 1 to the fourth minus 3 times 1 squared plus 5 times 1. Get rid of some of this stuff. Plus 5 times 1 minus 8, right? All we did was take this polynomial and put in and evaluate it at f equals 1. Okay, that's all we did. So this equals 2 minus 3 plus 5 minus 8. This is -1 plus 5 minus 8. This is positive 4 minus 8. This equals -4, which is not equal to 0. Therefore, x equals 1 is not a 0. And x minus 1 is not a factor. Okay, all we're doing is evaluating it. The other way you could solve it, I'm not going to do it, but you could solve it, is you could do long division. You could take this x minus 1 factor, try to divide it into this polynomial using long division, and see if you get a remainder. If it divides evenly, then it's a factor. But if there's a remainder, it's not a factor. Okay? Lorley, I know that this was a lot today. Do you have any questions?
I'm still have to view this, to watch this again, so that I can absorb.
I understand. It goes fast, and yeah, it goes fast, and we have limited time. and I want to make sure I cover something on every worksheet. So maybe find the section of the video when you're doing the worksheet, and that'll help you work through the worksheet. Does that make sense?
Yeah. Yes, yes.
Good, good. Well, I really appreciate you joining. If you think of any questions, or when you're going through the material, if you have any questions, send me an email and I'll be happy to help you out. I'll get back to you right away. Okay?
Yes, but I have a questions regarding the
Sure.
submissions on the solution. So, do I have to write it on a paper then have a scanned, or I would have to write it on the screen?
Most people just type it in. And they type, like, they use, like, you can see what I do is they'll use like a caret symbol. Like, if you can see my screen, like if I wanted to write something like, come on, if I want to write like x squared, I'd write an x with a caret squared. That's how I'd write x squared, or I'd write x cubed, x to the third power, like that. But if you prefer to submit your your sort of your work, the answers to questions, you can write it on hand and then take a picture of it with your phone and then upload that too. Either or, it doesn't matter. It doesn't matter to me. I'll look at it either way. I think as you look
Okay.
through, if you go into that discussion forum, if you go into there, you'll see what everybody else does, and you'll get a sense of how everybody else does it. And then from that, you can decide, do I want to, some people, they do a special document and then they upload the document. Some people just type it right there in line as best they can. Okay. It
Oh,
doesn't matter to
okay.
me. I don't care. It doesn't matter to me.
Yeah. Okay. Thank you.
Okay.
So,
If,
yeah.
if there's anything else, Lauralee, that comes up, please don't hesitate to reach out. Okay.
Yes, 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 of course. Thank you so much for the help.
Oh, you're very welcome. I hope you have a great day. And again, keep in touch. Let me know if there's anything I can do to help you. Okay. I'll
Yes.
stop sharing
Yeah.
and I will start. I will also stop sharing, and I'm going to stop my recording too. And then we